far away. Now I have to be careful what I say. But in this Markov history is usually very short. It's like 2 or 3 words. But funny enough, these type of modeling actually works pretty well in practice. It's no longer state of the art, but it's still not that far off in certain cases. Given you can actually find an optimal solution for this task using the Viterbi algorithm. I'm not going to go through it. I'm sure you guys have studied it. And anyway, it's not that relevant for what I'm going to talk. I lost focus. Okay. And there are also better models out there, as those models before, by the way, are called maximum entropy models. And there's a good reason for it. Again, I'm not going to go it. Actually, a very good description of this is written by Adwait, so he could talk about it to you if you're interested in that. He wrote a short pamphlet on maximum entropy, and it was in 1997.
A long time ago.
Anyway, yeah, but it was very good. I enjoyed it a lot. Anyway. So these models have the property that actually they normalize the probability per output. So for given a particular word, the sum of all the possible transitions or all the possible tags that you generate in that point, they actually sum up to 1. And that has some nice properties that it makes it a lot more tractable. However, unfortunately, it also suffers from what's called label bias problem, where you because of the way you're doing the computation, and you don't actually compute the whole thing going forward, but doing some sort of beam search where you reduce the number of hypotheses at any point, you run into situations where you get bad output. And one solution to this is use CRF models that don't normalize locally in every word, but rather they normalize for the whole sequence. And again, this is just a sort of aside. And there's I found that sort of, if you like neural networks, you can think of these models as some type of very simple neural network where you feed, for every word, you compute these one-hot embedding, which basically says that if I have, let's say, 20,000 features, I'm going to create 20,000 feature vectors that will have value either 0 or 1, depending on the feature fires or not on the word. And and then you multiply with a matrix, and then you sum them up and you get an output. You apply a nonlinear transformation, you get the output. And then you go to the next word, and you repeat, you compute this one-hot embedding, and you go on from there. Now, the one thing is you also have a one-hot embedding for the class to make this work. But you can compute these models basically with like simple neural nets. It's a little tricky because these models tend to have sometimes millions and tens of millions of features. So having these matrices might be a little cumbersome, but you can think of them as very simple neural nets. So a lot of times you want to bootstrap a new language, right? So you have some languages out there that have a lot of resources, and one of them is English. That has lexical resources such as gazetteers, and also it has annotated data. It has syntactic resources like Pantry Bank and onto nodes. It has semantic resources such as WordNet and entity label data and mock, ACE, CoNLL', those are all name entity data sets. FrameNet, PropNet, NumBank, onto bank, and so on and so forth. You can go on and on. But how are you going to, once you go to a new language, you probably don't want to recreate all these resources because it was expensive to create in English in the first place. And how can you leverage those resources that you have in English for other languages? And one solution to this, which has been proposed, as far as I know, the first one by Yarovsky in 2001, and I also have a paper in 2008 on it, you can use MTA for this. So how do you do this? So let's say that we have this sentence in Spanish, which gets translated to the Nepalese soldier was gunned down by former Haitian soldiers when they were patrolling the central area of Haiti, reported that organization, MINUSTA. Now, I actually translate, this is a automatic translation and is done, I took that example from the paper, so it was a pretty while ago. So the MT made an error there that did not translate patrol to, left it in the Spanish, patrolaba, I don't know why. But the point is that you can take the Spanish sentence, you translate it to English, then run the English system, and then you can push it back through the alignment to the original sentence. And here's another representation. So you take the Spanish, you produce the English translation, and with the lines are represented are the word alignment. Then you run your mention tagger on the English side, and then you propagate it through the alignment on the Spanish side. And then suddenly you have the labeling for Spanish, right? So this would allow you to actually get silver data, or to get an output from Spanish, even though you have no resources on the Spanish side, you only have the English. And of course, you have the machine translation from English to Spanish. So how well does this work? Well, it doesn't work that badly. So if, and we run experiments here in Spanish, Arabic, and Chinese, which are, different languages, different representations, different character size, I think it's a representative choice of languages out there. Also, it happened to be, we had data in A's for it. So, you're constrained to that to some extent. So if you do direct transfer in Spanish, so you take the English and project it to Spanish, you basically get about 66 F measures. This is, again, without any data in Spanish. If you use you also train the system. So if you start adding data in the Spanish, so assuming that you have, let's say, 100,000 words labeled, then the performance improves to 71 F measure. And if you have even more Spanish, then you can improve even more to 76. And if you do a voting between this last one and the direct transfer, you get yet another boost in performance. And the same story happens for Arabic and Chinese as well. So notable here, the direct transfer is lower, but as you add more data and you combine whatever data you have in the foreign language with this translated data, you get improvements in performance, which was nice. So that was about mention detection. Let's talk about a slightly different task, which is entity linking. So I'm not sure if you are very familiar with the task, but and if you are, I apologize because I'm going to re-describe it. But so the goal here is you have a database of entities, right? So that you already know. So you know that you have entities like Barack Obama, George Bush, Microsoft, Oracle, IBM, right? So you have all these entities with the representation. Let's say that, imagine that you have their Wikipedia page, right? So you have the entity linked with their Wikipedia page. And then you're given a new mention with the document, and you want to link it into the database. You want to find out, you have a new word here and you're talking about Clinton, right? With the document mentioning the word Clinton, and you want to figure out, is Clinton Bill Clinton? Is it Hillary Clinton? Is it someplace Clinton in somewhere in US? And there are a lot of towns named Clinton. Right, so that's the goal. Give it the mention, link it inside in the database that you have, and that's why it's called entity linking. You can also think of it as cross-document coreference because you are trying to coreference the word Clinton with whatever entries you have for Clinton. And so the point is to find the best assignment of an entity given a mention and a document. So we took this approach here where when you disambiguate a mention, you're also going to look at all the other mentions surrounding it, right? So and you'll see some examples that that's actually useful, right? So you can think of it, you're going to label this word based on what friends it has in the document. And so basically it's an assignment that assigns all the other mentions to their types and then producing the entities of those types given for all the mentions together, right? And then that will maximize over this whole mess. And it's very expensive to compute because you would have, if you have 100 mentions, then you have to look over all the possible assignments for all these 100 mentions, which is exponential. So you cannot do it. So instead, we looked only for a few of them that are surrounding within a window of 20 words, let's say, and that reduces the size a lot. And we also only look at the top 100 labels for each mention, and then we build a maximum entropy model to produce this probability, the entity assignment probabilities. And in terms of features, we looked at things that are text-based, such as cosine between the entities and the mention, the Wikipedia page, if you want, and the representation of the mention of the document, and various combinations of this with their centroids. We looked for knowledge-based link properties. A lot of times the Wikipedia, for instance, would give you links to other pages. So we would look for links from dimensions in the Wikipedia page to other pages to sort of see if they're connected here. We're looking at the title base, then entity pair features, and so on and so forth. And the one interesting part here is that neither of these features are lexical. So we're not actually looking for specific words, but we're looking for, we have the example side, and then we have the database side, right? And we're looking at some combinations of features there, but we never actually identify words in here. Like when you compute the cosine similarity, you're looking to see if the words match, but you don't care what the words are per se. And this is going to play an important role later. And here's an example, right? So you have a sentence saying Broad catapulted England to a 74-run win over Australia. Now, the words highlighted here can have multiple types, right? I mean, Broad it could be a person, but also that there's apparently a few people named Broad in the Wikipedia. It could also be not a name, but in here we sort of assume that we know already that this is a person. And then you have England and Australia. In general, countries play several roles, and if you look in Wikipedia, you'll have several entries for these words. In particular, I mean, you obviously have the countries, but in here they're not actually countries, but rather they're teams, right? And turns out that this is a cricket team, and I know this because I know the example, but I'm not sure if it'll be clear for anybody reading this sentence that we're talking about cricket. But anyway, so yet another example here where when you compute the cosine similarity between the input document and the Wikipedia page of Stuart Broad, you get things that match there, such as England and seam bowler and so on and so forth. And then there's apparently another Neil Broad, which is a tennis player for South Africa or Great Britain. Then there's not so much overlap here. So you're gonna like Stuart Broad from Neil Broad just because there are a lot more word overlap. So the cosine similarity will be better between these words, between the input document and the Wikipedia page. And we have other global features such as category relation count and entity category. But in interest of time, I'll skip over those. And the interesting thing that it hit us at some point is that because neither of these features are lexicals and they only compute associations between two string texts, then the parameter language you can learn about these features can in fact transfer across languages. So basically, I can learn the system on English and just apply it on Spanish, and it'll work just fine because you can compute the cosine similarity in Spanish. It doesn't matter that the parameter was trained on English. So basically the results. Anyway, so we ran on a few data sets. Some of them are standard ACE, MSNBC, and TAC, which stands for Text Analysis Conference, and compared against the state of the art at the time, which were a bunch of Wikifiers and entity linking systems. So let's see how we did that. So was computed in English, Spanish, and Chinese. So the system I'm talking about is the LEAL, the last column here, and it did better than other systems out there in English. And this on the left is on a few data sets that I mentioned earlier, and on the right is about on the TAC evaluation systems. So in this system in Chinese, for instance, it was trained on English and applied on Chinese. It did not see any Chinese data during training. And it performed just as well as the other systems. In terms of numbers, it's slightly lower than the other, but when you compute a variation, like how those things vary depending on the training data size, you can get a sort of an approximation on what's the system performance, and all systems were within the variance limit. And also in Spanish, the system did better, did quite well, even though they didn't see any Spanish.
A quick question. When you're saying that these systems were not trained on the language-specific data, that's because you used the translation method to. No.
So this was the systems themselves, right? They're only so they're computing some measures that do not look at lexical representations, right? So they're computing cosine similarities between the input document or some snippet around the mention in the input document and the Wikipedia page, right? And that cosine similarity you can compute in Chinese if you want, right?
Oh, okay.
And the features themselves they turn out to be resistant when you go across language, right? So if you figure out that the cosine similarity is important, it will be also important in Chinese.
Okay, so this is purely on language independent features.
Yes, you're purely on language independent features, and we just computed those features in the other language because you could.
Okay.
So that was interesting about this method. We avoided as much as possible any lexical features. So then you can do these things. And the system that performed pretty well on the TAC data compared to the systems that are unlabeled, our system that participated in TAC, and we didn't give them names because TAC is very adamant about not comparing systems. So anyway, but the point is that the performance is quite a bit better in 2003 and 2014, 2013 and 14, compared to the top system at the time. Okay, I lost my focus. So let's go back to mention detection and move on to neural networks. So when you do NLP with neural networks, what you do is usually you take the words and you embed it into some space so they become vectors in some high dimensional space. And this was the work I'm going to talk about here. It was done at the time, like straight after Mikolov came up with this word embeddings, the SIBO and the skip gramming embeddings. So the networks are not deep; they're not transformer-like, and we'll talk about that later. So the standard ways of encoding these words. So the nice thing about it that was discovered is that you can train the embeddings of the words. You can train them in an autoregressive fashion without actually needing any data, except you need unlabeled text. So the way you do it is that you take a word in context, you mask it, and then you use the surrounding words to predict the current word, right? So you just mask the word and say, I'm not going to tell you what it is. Here's the word surrounding it. Try to predict the word. and this is called SIBO. And then there's a version of it that goes the other way around. Basically, you form a word, try to predict all the words in surrounding. That's called skipgram. And we had yet another version of SIBO, if you want, where instead of actually, so when they do this prediction from the surrounding words to the next word, what they do, they usually take the average of the vectors. I don't know, they like to do this. We found out that it's better if you concatenate them as opposed to taking the average. But anyway, it's a slight variation on it. So how do you decode with neural networks? As I was saying, you feed the network these word representations, and they go into the network, and there's several layers of hidden representation and nonlinear transformations. And at the end, per word, you're going to produce something that says, this starts an organization, continues an organization, starts a person, and so on and so forth. And here's an example that says the 21st Century Fox said in December they had reached a deal to take full control of Sky. And those are the labels that you want to find. Those are the true labels for this particular sentence. So the decoding works, you feed in 21st, and it runs through the networks, and it produces begin organization. Then you run century, and it runs through the network and produces inside org. Then you run Fox, and it produces inside org. Then you run sed, and then produces start event communication, and so on and so forth. So the output themselves, it's a stack. I showed it as a stack, but it's not corresponding to individual entries. Those are all the possible labels that you can get. So for every word, you get one output. It's one of those. I was just highlighting which one it is. And this method actually turned out to do pretty well compared with the previous maximum entropy models. And compared with CRF, and you can see that it's we've run on an internal data set called CoNLL'03, the third version, the iteration of it. And if you compare systems within domain, so if your test and training are in the same domain sort of thing, then CNNs do slightly better, but not a lot better. However, if you feed it data that is out of domain, they tend to be more robust. So I think in here we had a data set that we labeled specifically just to try this on political party association, which was not really part of our initial training data. And also the system performed pretty well in competition in the TAC 2015 evaluation. I think it was ranked first for both English and Spanish for mention detection. And you can see the comparison of the system. It was actually, this was a combination of the neural nets and CRFs. And it was better than both. Because that's what you do when you just want to improve your system, have them vote. Okay, so how do you bootstrap a new language with here? And this is, again, the MT idea. So I showed you this before. I'm just showing you with a new data set. But in here, you can actually do something interesting, which is you can actually do zero-shot projection. So this is a funny thing that is discovered at some point, that you can imagine that a language is some sort of distorted projection of the other, right? So if you have these vector representations for the word, I can actually obtain vector representations for a different language by looking at a dictionary and then learn a mapping between the two, right? So you have the vector representations in English, and I'm going to produce some vector representation in Spanish that are just a linear mapping. I'm taking those vectors and multiplying by a matrix. And you can compute this by using a method invented by Mikolov that is basically looking at minimizing the least square distance between the output of the matrix and the real vectors in Spanish, right? So you assume that you have word vectors are represented. You learn those things both in Spanish and English, and those you can learn always because they don't require label data. Then you learn this mapping between the two vectors by linear projection. And this also allows you to do zero-shot language mention detection, which is basically you take the Spanish, right? You take the Spanish embeddings, then you multiply with the matrix, and you get these sort of fake English embeddings, or Spanglish if you want. And you add some other features, and then you run them through the network as before, and then you get the results, right? So, and you can do these projections in two ways, and I have numbers for both. So one is just, I'm going to take some word in Spanish and I'm going to project it into something in English. It might not be a word, might not be even close to any word, but I'm just going to take it and run it through a network. Or instead, once I project it, I'm looking for what English words are actually similar to these words and replacing that by some average of the vectors of real English words that are surrounding this projected vector, right? And then pass it to the network. So how does this do? So just to start, in light blue all the way to the right are the performance that you get if you train in the language, right? So if you actually train in Japanese on the clue data, then you get 82F measure, right? But we're looking here as how well can we do by not having any data in Spanish, but or Japanese or Korean, but instead learning some projection between Japanese embeddings and English embeddings, and then applying the English model on this projected data. So if you just do direct transfer, this is the machine learning method, I'm sorry, machine translation method before, then you get the results in dark blue. And they're the lowest of all, most of the time. There are some cases where it gets better in the CoNLL data set. Then you can do the projection transfer, which you take the embeddings in the foreign language, you project them to English, and you just run the network. Or you can do the interpolated transfer, where you do the projection, then you look for other words in English that are similar to that word, and then you run the network, right? And so the interpolated is orange, and the projection is gray. And between these two, sometimes the projection is better, sometimes the interpolation is better, but if you combine the two, is always better. So that's good between the two. So what's interesting here is that for a lot of languages, you can get quite a bit of performance by not seeing at all results in the language. Like in Portuguese, the combination method gives you about 70 F measure, while the system trained on Portuguese gets you about 75. And by the way, the system trained in language is the same neural network that was trained, but it was trained with actual Portuguese words as opposed to the English network. So that was exciting. So I have until, when should I stop?
I would say you can go up until about 4, maybe just before 4, 350 to 4. And then
okay, so you have like 20, half an hour.
Yeah.
Okay. I might finish before that anyway. So, okay, let's move on and talk about slightly different tasks. And I'm going to merge here coreference resolution, entity linking, and relation extraction. So, remember we talked about entity linking already, and we're talking about these features that are language independent. Now, those features were combined using maximum entropy, but nobody stops us from using an actual neural network to do this combination, right? And that's what we've done here. So we took all these cosine features and all the other features that we predicted before, you put them together, and then we pass them through this multi-perceptron binning layer, and I'm going to talk about it later, because it's an interesting concept, actually. So basically, you have these numbers, and you pass them through this layer that sort of tries to normalize them in a way that sort of makes sense. And we also can in here actually add word vectors, and we'll see how we're going to add those. And then you have the query context, and you have the wiki context, and those get combined. And then all these features get put together, and they run through some layers of neural network, through softmax. And in the end, you just predict Are they linked or are they not linked, right? So it's not that much of a difference from before, except that instead of using maxent, we actually used a neural network with proper layers. So I was going to mention this multi-perspective binning. So what it does, you take the context from the query and the document, and those are word contexts. So they're variable contexts. You could have whatever the number of words you have. And you want out of this to come up with a fixed size, right? And a standard way to do this is to do convolution. Convolution allows you to take long variable size representations and sort of converge them to a fixed size representation. And so we did the convolution, then we take a mean pool, then we take a tangent, and so we get these fixed vector representations for the query context and the target wiki page. And then we compute a similarity. Now in here, interestingly enough, instead of computing direct similarity, right, so instead of computing cosine similarity, we can use this called multi-perspective similarity, which basically allows individual directions of these vectors to vary, right? So you take you assign a weight for every direction, right? So if the vector has 300 elements, then you have 300 variables that allow you sort of multiply both the context and the Wikipedia page sort of representations with these vectors. And with those weights, and the weights are trained. So it allows you to customize a little bit the cosine similarity, because otherwise cosine similarity is pretty much fixed, right? I mean, you're just throwing these weights in, give the system some tuning parameters so to sort of improve the performance. So how does this do? And I'm showing here 3 results. One is on a CoNLL 2003 data set for entity linking. This is in English, and the other 2 are Spanish and Chinese. The top part of the table are results from other papers. By the way, the ones that I was talking about earlier is Radu Florian that has 86.2. That was the initial one that we talked about, the maximum entropy version of the entity linking. And you can see that the the world has advanced a lot in 2 years. It went from 86 to 93 in terms of performance. And this neural network does even better, it does around 94. In Spanish, also, the system improves quite a bit versus other systems in the literature, and also in Chinese. So we had this the state-of-the-art results in 2018, I think, in AAAI at the time. Okay, so that's cross entity linking. Let's talk about coreference resolution a bit, right? So
quick question. I thought before we switch topics, do we want to pause just to see if there are any questions on those?
Oh, I'm sorry. I should mention this. If you have any questions, please interrupt me at any time.
Okay, thanks.
It'll make my day.
Go ahead.
How does the performance regarding the computing runtimes and latency stuff for during inference or training?
Which method? So maximum entropy methods are pretty fast to train because they train the features independently. Neural networks, I think these ones were not bad. I mean, these particular ones would take like half an hour to train. Also, they were based on really old technology. This was I think they were implemented in Theano, because that was the thing at the time. I'm sure that if you re-implement them down in PyTorch, they'll be a lot faster. Or TensorFlow or whatever you like to implement them in. So in training time, inference time, they're pretty quick. I'm interested in like words per second or something like that. I don't have them. But they would return things in real time. They would definitely return the answer faster than you could get it. That's for sure.
Thank you.
I think there were sub-second times, right? So they would take milliseconds to run. Transformers are a little slower, but even those are pretty decent. It also depends a lot when talking about neural networks is, do you care about latency or throughput? Because in neural nets, you can batch things, right? So you can run multiple things at the same time, and they're going to run just as fast as running one thing through, because the systems are so nicely parallel. So if you're caring about processing a lot of data through, then it's much better than if you run one at a time. So if you have a user interacting, you'll see lower latency. I mean, the latency is going to be acceptable, but if you're trying to process them that way, it's going to take a while. But if you batch them, they run very fast. I don't know. Does that answer your question?
Yeah. Yes.
Okay. So coreference resolution, what is this? So basically it's the task of grouping mentions into entities, right? And here we have a document talking about the Bush dynasty. It's talking about Jeb Bush and George Bush and yet another Bush. And it's related to entity linking because in here, right, you have Jeb Bush and then you have George Bush. And then suddenly you have this other Bush, right? And the question is this the older brother or is the younger brother, right? So it's also related to linking because you want to link this instance of Bush to the right version of it from Wikipedia, right? So basically, do you want to link this Bush with this Bush or however, and then the links here are done correctly. Okay, and there's a lot of synergy between the coreference resolution and entity linking because you cannot really easily resolve nominals and partial names without entity linking has trouble resolving them because there's not enough context, right? I mean, if you have president out of context, you don't know which one it is, and it's harder to do. However, coreference resolution is sort of meant to do that, right? So the strategy we came up with, which is a pipeline strategy, is first use the coreference resolution to cluster mentions into entities. Then identify the canonical mention for each entity, and usually it's the longest name entity, right? So if you have, let's say the entity only consists of Jeb Bush and Bush, then the representative will be Jeff Bush, right? And finally, once you have this, you can use entity linking to disambiguate the canonical mention for each entity in Wikipedia, and then all the chains will be, by the way, we call chain the sequence of mentions that are in the same entity. Okay, and basically is what I said. Okay, so in here we use state-of-the-art cross-lingual neural Yale system at the time, I should say. And then the coreference resolution system is also entity-centric and cross-lingual, and we'll see that interestingly in here, there's almost no loss in performance, which is amazing. There's no loss in performance going from English to a different language, which is, it was mind-boggling to me at the time. And we also evaluate the coreference resolution system independently and in the context of doing entity linking, okay? So the coreference model that we have is entity-centric. And what I mean by that is that we basically, the model at its core has, can compute the given a pair of entities, it computes a probability whether they are coreferent or not, right? So to use this model to actually generate the entire coreference resolution, what we do is we start with each mention in its own entity, and then recursively as we go along, you look for every entity. Remember, the mentions are its own entity. So we find for entity E1, we find the closest, an entity E2 that has the highest link of the highest probability of being linked. So the probability of link given these two mentions, these two entities. And if this link probability is higher than 0.5, then we're going to merge E1 and E2. Otherwise, we leave E1 alone. And we stop this when there's no more merges possible. Okay. Any questions on this? Let me give you an example. Maybe if it's unclear, it'll become clear here. So here's the sentence we had before, and we have here four. Actually, this is a different mention. Sorry, this is something about President Bush that lost private jobs over the course of 8 years, while President Obama has created some number of private jobs during his presidency. So we have 4 mentions here. 2 of them are president, happens to be different presidents, and then you have Bush and Obama, right? So first we resort the mentions, because nobody says which order I'm gonna examine the entities, but it turns out that it's better if we start with named one first. So I'm gonna reorder them. So we look and I'm gonna put the named ones first, but still in the order that they show up in the document, right? So Bush, because it's the first entity, I'm gonna skip. And when we're at Obama, we're gonna look to see is the entity Obama correct with entity Bush, and we're saying no, they're not, because hopefully the system decided not to put them together. So we're gonna leave the same. Then we move to the first president, and we're gonna try to see, does that president link with Obama, or does it link with Bush? And we'll find out that it links with Bush, so we'll put them together. And then we're going to go for the second president, and we're going to check to see if it links with the entity George Bush and president, or it links with the entity Obama. And we decide they're linked together. And at this point, we'll find out that these 2 entities are not mergeable. So we're going to leave them the same. And this is the output of the coreference solution. So how are we going to compute? So we're going to build a network that computes this probability. So as the input, we're going to have the 2 entities. And so not only the words in the mentions in each entity, but we're also going to have the context for them, right? So you're going to have some variable context for them. And when you compute we're going to run convolution on them to get a fixed size representation. So then we're going to compute these intermediate layer that is based on the pairs of mentions in the 2 entities. Then we're going to have a ReLU layer to have a nonlinearity there. Then we're going to have an attention layer. So we're going to have here different values for pairs. And so we're going to do this computation based on whether the mentions were named or nominal separately, because it turns out to be better. And we're going to have an attention based on the fact that they were named or nominal. And then we have a pooling layer that just combines these things, and a sigmoid layer, and finally an output layer that says yes or no. Okay, so this is the neural net. So again, the features computed here are pretty language independent. We actually don't, all the features are computed on pairs of texts, like cosine similarity and so on and so forth, and those can be done across language without issues. So we can train the system on English data and then apply it without any training on a new language, right? And this is what I said before, because the features are language independent in the end. And so we train our coreference solution system on English using English word embeddings. I think those were the SIBO embeddings. And we apply this transformation for foreign languages, because the system was trained in English. We need to project the foreign language onto English. And we use the projection that I described earlier. So we have 2 evaluations. One is intrinsic, which is we're going to compute the coreference solution scores on gold standard mentions. And extrinsic, where we will evaluate coreference as an end-to-end entity linking pipeline of mention detection, coreference, and entity linking, right? So you're basically giving the documents, and then you have to, for every mention, you have to link it to the Wikipedia page. That would be the evaluation. It's interesting because it actually doesn't look at coreference separately, but rather as how does it impact the entity linking. Okay, so this is a comparison with the state of the art at the time, which we retrain on the stack data set. It does quite a bit better on the CoNLL score. So how does it do? Now, I'm showing here the performance of a system trained in the language versus the system that was projected from the foreign language to English and then run the coreference solution system. The blue one is the projection. The light teal one is the one that was trained in the language, right? So I blew up the scale here. They're very small differences, right? So in fact, running the English system on Spanish only lost 0.5 F measure, and running the English system on Chinese lost 0.3 F measure. That was really surprising. So basically, you can get a system in Chinese by just running the English one and projecting the Chinese into English. With a very simple projection, by the way. We're not talking about machine translation. This is word by word projection into English. It's really weird. Honestly, what does it so well, but you really cannot really argue with numbers. This is the evaluation of end-to-end system. I
think we lost audio.
I think it just froze up.
I'm sorry?
Oh, I think we lost audio for a second. You might have frozen up.
That's possible. Hold on, I need to get a charger. I'll be 2 seconds. Okay. So in green was the combination of coreferences in that year. And finally, the last system that we presented before is the one that we converted the features of the entity linking into a neural net. So the red one actually takes true mentions as input, as opposed to the green one that it produces the mentions and runs coreference on them. Any questions before I move on?
I think the video of your face is frozen, but I think the screen is okay. But so we can just go on as it, but just wanted to let you know.
Well, that's just my face. I'm sorry.
Okay.
I can speak without moving my lips.
Okay. Okay. That's a nice trick.
Yes. It's a performance presenting. Okay.
Any questions? Stop or from the class? Okay, go ahead. Why don't you go ahead?
Okay. And those are what I said, basically, that the English combination outperforms the entity linking alone in both Spanish and Chinese. And it outperforms the best tax system at the time on both Spanish and English. And it's competitive with state of the art that uses training data for Spanish and Chinese, right? While the green one only uses the English data that they're projecting from English. It's rather impressive that you don't lose that much performance through projection. Okay, relation extraction. Actually, let me skip. We've done something similar. It works well. And I'm gonna skip just because I want to get to here, which is the current state of the art, which is the attack of the transformers. And in case you're wondering, it's just the attack from Sesame Street. So there were a lot of, with the introduction of transformers, and then I'm talking about Multilingual BERT and XLM Roberta and MBART, MT5, and so on and so forth. They're funny enough, they created intrinsic alignment of words. And in general, English variants themselves, I mean, even transformers themselves are much better performers than the previous BILSTM models. And they introduced this mode where it's very, very easy to do multi-language models. So before, remember, we had to have this projection that we need to learn. And by the way, the projection, I didn't mention this, but it doesn't actually require large vocabulary. It turns out that 500 words or 1,000 words is good enough to learn the projection. So it's not very onerous in terms of resources. You just need 1,000 words. Aligned dictionary, and obviously you need the word embeddings in the language, but those you usually can get. But the transformers really simplified things a lot, as we'll see. So here's an example of how transformers work. And again, for some reason, the word at I guess I use a different font. So what it does, so it does a couple of things. One, before we were analyzing entire words, so we had embeddings for entire words, but this will create large embedding size, right? So if you get the standard embeddings, the SIBO embeddings, or the ones from Stanford, skipping the name right now, they have about 300,000 embeddings, right? And this was only for English. So if you want to have embeddings for a lot of languages, you're going to create really huge vocabularies that will create issues. So instead, what they've done here is that they break down the words. So you take the words and break them into what they call word pieces. Like, for instance, in here, we have the word rejects. It gets split into re-injects. And yes, those are not really words, but apparently it doesn't matter. And you add a symbol to specify that you actually split the word. Like there's later the words boycott and got split into boy and caught. And basically what those models are, they can build on much larger real vocabularies by doing these splits, because they only keep, so for instance, the XLM Roberta, which was one of the larger ones, has about 250,000 word pieces for 100 languages. So they've done this for, they break languages, all the languages into pieces. So what they do, so basically they take these words, they split it into word pieces, and then they pass them through a series of transformers where the representation is modified based on the words and surrounding. And I'm not going to go into details how they're computed, but it's a very smart way of doing it by using attention. So basically you move at every layer, you get more information from the context and put it into the word. And you keep doing this up until the final layer where you actually do the prediction independently. So you moved enough information from the surrounding context into your own representation that you're able to predict the type of the word piece. So in terms of training, they also have an interesting method of training. And those are bidirectional language models, right? So some of them, if you train a BERT model, you look at the entire sentence. What you do is you take a word and you mask it, right? You say, I'm going to pretend I don't know this word. And it could be a word piece, or it could be multiple words, whatever it is. There's multiple ways of doing this. But the point is that you hide that, and then you train the system to repredict the value. So it's an extension of the word embedding strategy, but it's much deeper, right? So you have, instead of having one layer, you have either 12 or 24, or if you go higher with GPT-3, you have, I don't know, 48, 96 layers. So there are a lot of transformations that you go through, right? And funnily enough, if you run this on multiple languages, because you play the same game of hiding the word and predict the word, of hide and seek with the word, you basically, the words get aligned, interestingly enough, right? So the, yeah, I don't know. These methods actually work, as we'll see, interestingly. So I have an experiment here where I just took the multilingual BERT model and just train it on, I have multiple ways of doing experiments, but one of them is to basically, I wanted to see if I train one model out of all the languages, does it do better than individual languages? I mean, does it work at all, right? Because who says that if I train English and Chinese together, I'm going to get anything? And then two, if I take the English model, how does how well does it do if I just apply it, if I feed Chinese through it? And the nice thing about it here is that we don't need to do any alignment anymore, because through the nature of training these BERT models on, so they're trained on 100 languages. So they took all these languages and segmented and just train them together, right? By training together, meaning that they fed to the system Arabic and English and Chinese and so on and so forth. Now, it was not mixed in any way. They're fed independently, but they run through the same network, right? So the network is what is constant across languages. It's not, they didn't do translation or anything of this type. So how well does it do? Well, it turns out that the multilingual system does better than individual systems, right? So in blue is a system that was trained on the language, in English and Spanish and German. And the green one is the one that I put all the data together and train one model, right? So it does better than all the languages, including, interestingly enough, in English. And it does has better performance improvement in other languages, in some languages than others. And here's a comparison with other models at the time. I'm going to skip it. It does better overall. And here's an example of the same thing on OntoNotes. Now, the difference in OntoNotes is that these languages don't share the same vocabulary. So in CoNLL, they actually have the same vocabulary because you had English, German, Spanish, and Dutch, right? So they all use Latin alphabet. But here, Arabic has its own writing system, and so does Chinese, and they don't overlap at all with English. And it turns out that if I train a system that I feed English, Arabic, and Chinese, it does better than each individual language itself. And this is, again, a comparison with other systems out there. So in here, in Arabic and Chinese, we had the best results at the time. In English, there was a system that was better. And here's yet another system. I'm going to skip this if you don't mind. So if we go to low resource and zero shot setup, right? So what happens if I take the CoNLL data, right? Then I just run all the languages through English, okay? And here's what happens. So the first two are outputs from state of the art at the time on German and Dutch for zero shot. So if the first line, this one here, is basically I'm gonna feed everything through the English model, right? So the German gets 75 F measure, Dutch gets 78, Arabic does 10. Those are on CoNLL, and the ones in blue are CoNLL, and the ones in green are OntoNotes. Now Arabic, it turns out that it does pretty badly, and we'll see later there's a reason for it. And it's not necessarily having to do with the method, but rather probably in the way they generated word pieces for Arabic. And surprisingly, this number is amazing, okay? So we train a system on English and we fed Chinese to it and we got 65 F measure. That was mind-blowing at the time. We had to repeat the experiments a few times just to make sure that we're not wrong. But it turns out that that's on that data set, that's what it does. And just I'm going to show you the number on Chinese. So if you train everything.
We have a question in the audience.
Yes.
So we are saying that when we fed English, when we trained the system on English and fed Chinese, so what exactly did we feed Chinese? So are we feeding one-hot tokens, or is there an embedding of some sort that we are feeding to the system when we are predicting for Chinese?
Right. So the way transformers work in general, they take a piece of text, and the same thing happens in Chinese, except that it's there is some tokenization that happens, and all the packages out there. I mean, there's a Ribera tokenizer, there's a BERT tokenizer. So what it does, it splits that text into word pieces, right? In English, I showed you before what happens. Some words get split. In Chinese, they will be tokenized into word-like units. I don't think they're really words in Chinese, but they're word-like units. And those words are the ones embedded, right? So it's really the text gets fed to the token, to the transformer through this process. There's no projection or anything. It's just you take the text, you break it into pieces, and then you look up the pieces. They have embeddings for every of these pieces, and then they go through.
And also, can you give an intuition of why this is happening? So why actually training it on two systems works better than training on one system separately? So what exactly is it doing internally? Is it learning some rules somehow?
Here?
Yeah.
So let me start with, I'll talk about this because here maybe the situation is a little clear. I think the same situation happens for the other languages, but I don't have evidence. But here, you can imagine that I have the English data, right? And the Spanish data is independent, right? There are not translations of the English data. And it's possible that in Spanish, I have some other mention types, or like other names of people that I didn't see before in English, right? So adding that Spanish data to the English data helps the system a little bit because it finds these other people being, these other strings being people, right? And organizations. By the way, this doesn't work for everything. Most specifically does not work for country names. Country names are really translated in every, so, Germany is called Allemagne in French, but it's called Deutschland in German, is called Germany in English. So they don't have the same as lexical representation, but people don't usually get translated, right? So Barack Obama will be Barack Obama in English, Spanish, German, or Dutch, right? So so I'm making this hypothesis that because the system does the same work to train, it learns to align the words across languages, right? Because you're forcing all the languages to go through the same model. It will learn that this word piece in English is very similar to this word piece in Spanish and German and Dutch. And if that's really the case, then I really am getting more training data once I add all the languages together, right?
So, and this also works with English and Arabic, right? So even though—
Yes, exactly. So that's I wanted to start with that's easier to make. And yes, assuming that what I said is true, it also will do it for Chinese, right? So they will find characters in Chinese that are similar in sort of, they will be embedded in things that are closer together. And adding the data together will give the system more training data. Now, I think an interesting, but I could run this experiment where, so I'm really making the hypothesis that the size of the training data is that matter. So I could take less English training data and sort of do that experiment. So take a third of English and combine it with a third of Arabic and Chinese, and then take the whole English and how do they compare? right? I mean, it's actually probably a third. If you train the system on only a third of English, you're going to do worse than. But I think this is what's happening in the end. You get more training data. Even though it's in a different language, it's sort of BERT normalizes it in the same space. So this is what happens if you actually train, or you pass it through English. So we tried something else. We also tried for every language to train a system on the other three, right? And then test the system. And that's the entry here, right? So for instance, I train on German, Dutch, and Spanish and test on English. And I train on English, German, and Dutch and test on Spanish, right? That's the sort of a round robin we did here. Interesting enough, it does well. It does worse on German, but it improves slightly in the other cases. And then we try to see what happens if I add 15 sentences in the language, right? So we took the English system and added just 50 sentences of a language and see how it improves. And you can see that Dutch improves quite a bit. There's a big jump here in Arabic. Chinese improved a little bit. And then what happens if we add 50 sentences? I think this is additive, right? So it's plus 50 plus, so it's this is 100, this is 150. So you can see that the Arabic actually improves decently well. So I was saying that there's something funny going on in Arabic. So remember, I was talking about how we take these words and we split them into word tokens, right? Then you can look at this measure of fertility. It's basically for one word in the language in one space separated token, and how many pieces does it break? And it varies. It turns out that for English, Dutch, and Chinese, they're all about the same. It's 2.5, 2.3 to 2.5. However, for Arabic, it's 7.4, right? So I'm not even sure exactly what's happening here. But Arabic is an inflective language, but I'm not sure that 7, I think they've split them into characters, honestly, a lot of times. So it doesn't, if you split them a lot, they will not align as well with the other words, with the other tokens, right? So that's why you do poorly, but you start to catch up once you start adding things from Arabic, it sort of learns how to deal with them and sort of the performance improves.
Hi, Hans, just a time check. Do you want to maybe wrap up in the next few minutes so you can leave time for discussion?
Great, so the conclusion is the slide that I want.
Oh, perfect.
So it took only 18 years for the CoNLL objective to actually be realized. Woohoo! I guess we're going to completely solve the problem in the next 100 years. And this is an interesting observation. If we would have the technology at the time, if we fed the zero-shot MBERT, would have won CoNLL 2002 and 3 in German, Dutch, and ranked second in Spanish. Okay, so this is the English model that we just ran on the other, pretending the other languages are English and just pass them through. Would have won the competition at the time. Just to show you the trajectory of improvements that we've seen in these 18 years. I really believe that these multilingual models are awesome. They're not perfect, and underrepresented languages do not perform that well, but it does allow you to build models, even if you train only on English, they will do not trivially, they will do decently well on other languages. You obviously can get better if you add data from the other languages. Okay, and I'm going to end up here. Saying that we are investing $25 million building a large GPU cluster of A100s to build large language models. Okay, so I'm ready for discussions.
Okay, let's thank the speaker for a really great talk. Recording.